r times the velocity of the exhaust relative to the rocket. And this, a lot of you are students in engineering. You may already have actually talked about this. Anyone know what this combination of two variables as defined is actually typically described as in engineering settings? This is actually the thrust of a rocket. Okay, let me just talk about this, and we're going to come back and do the whole thing. All right, so let's say we've gotten to this point, and I know we have to come back and talk about it. I'm simply going to divide by dt and look at what we are left with. So first off, on the left side, we're left with the mass times the acceleration. And remember, this is now a sort of instantaneous expression, so we're talking about the mass times the instantaneous acceleration. This thing on the right-hand side, well, minus dm by dt, dm, you'll recall, we somewhat perversely defined as being negative. So minus dm by dt is simply the rate at which we are essentially expelling or using and expelling fuel, the rate of fuel consumption. And so if I cast this as the rate of fuel consumption, what I learn is that I get a practical expression for the mass acceleration of the rocket in terms of the rate at which I'm burning fuel and the speed at which I'm injecting the exhaust gases out of the back. So this turns out to be a useful parameter for rocket builders, because in some sense these two things are two of the things that we can have very sort of clear control over when we're building a rocket. All right, so let me pause here and come back and see if we can just recap what was done. All right, so slightly perverse but perfectly consistent definition of instantaneous changes in a time interval dt. The mass changes, yes, it actually decreases for the rocket, but we're writing it in such a way that it looks like it increases. So the mass changes by an amount dm. That dm is expelled out of the back, and these things have velocities. In this case, everything's measured with respect to some external reference frame. Okay? So all of that looks pretty straightforward. Modulo the strange notation, why did I write v prime, v plus dv, and modulo the fact that we chose dm to be negative. But you should be pretty comfortable with this. There's momentum conservation. Okay, now a little bit of change of variables, making use of the relative velocity. So this is now talking about the velocity of the exhaust relative to the rocket, or the rocket relative to the exhaust, the way it's defined. But of course we can express that in terms of the two outside or externally observed velocities, and that's what we do here. Okay? So the reason this is done is simply because it's this parameter that is useful for actually rocket builders, for them to know at what speed exhaust gas is being expelled from the rocket, rather than any external speeds. Of course, those things are environment and time dependent, depending on the environment the rocket finds itself in. So this is something that's very specific to the rocket, which is why we're trying to extract it here. Okay? So that's why this becomes a focus. Now, I need to apply momentum conservation in some inertial reference frame. Again, another reason why we're looking at things from the outside world, like this. A little bit of substitution in terms of now variables that we've used. Plug it into momentum conservation. There's nothing new here. Just plugging in some kind of weird looking algebra. We end up with this. Simply divide by time to get something that's explicitly time dependent, and then get it in terms of things that we can actually sort of work with, so to speak. So let me pause there and ask questions, because I guarantee there's a bit of confusion. Yeah?
So the relative velocity is the rocket relative to the exhaust?
Correct. Okay, so that's the one velocity that is relative to something other than some external inertial observer. Yeah?
Can you repeat going from the second, the v prime there, yeah, going from there to the next, can you repeat how
this is simply a substitution over there. So here's my momentum conservation way up top. So all I'm doing there is taking the second line down. That corresponds to the first term on the right, but I'm opening out those products of two pairwise parentheses. That's those four terms. And then I'm doing minus dm times v prime, which v prime now has three terms. So it gets carried over into here.
So what is the v on the left side?
So that's the initial velocity, simply this, at some early time. So we're looking this at just some small time interval, okay? So early time, later time, some small time dt later. So that's just the initial velocity, and then we're going to be looking at this kind of, how do I want to say this? We're simply looking at this at a sort of given time. And of course that's going to be changing. So that's going to change continually. Yeah? Okay, I see not great sort of satisfaction with this. I know it's a weird way to approach it. There's no way you would initially set things up and choose to do it this way, but I want to make sure the motivations are clear and the punchline is clear. Motivation, momentum conservation, fine. No external force acting on the system. Yes, of course there are forces internally, but no external forces. We're in free space. Momentum conservation from some inertial reference frame. So it's essential that I talk about velocities as measured as some inertial observer. Again, weird notation. I think just the notation here is kind of, it's sort of traditional, but not maybe hugely helpful. And if I did it completely differently, you might be happier, but then when you read your textbook derivation of this, you'll be unhappy again. So I followed it with slightly different notation. So that's why I need set up momentum conservation with respect to the outside world. This choice is a little weird, but fine. It's logically consistent. Apply momentum conservation, and then simply do some relative velocity definition, because remember, my momentum conservation has to be with respect to an external inertial observer. But in practice, the thing that I know about when I'm building a rocket is how quickly exhaust gas is being expelled out the back of it once I power the thing up, which is why this kicks in here and why it's useful, because it's a parameter that we're actually going to build into the rocket. So that's the motivation, some manipulation, just back to momentum conservation, simplified, divide by dt to get some instantaneous quantities. We do a little bit of variable redefinition in terms of the rate of fuel consumption, and this is what we're left with. Okay? So, turns out the mass times the acceleration can be determined in terms of the rate at which we're burning fuel and the relative velocity of the exhaust gas. These things are designed into a specific engine design. These are fixed for us. What does that tell you about how the acceleration changes as the rocket continues to burn fuel? Right, because the mass is decreasing over time. Okay, so mass is decreasing as the rocket fires. Since this is a fixed quantity, presumably for most rocket designs, or at least we consume this constant, this tells us something about how the acceleration changes with the mass as the fuel rate, as the fuel consumption goes down. All right, so one last thing on this. It's kind of useful. So I'm going to come back to this. I kind of feel I need to give this a punchline that makes it less confusing. So the reason for this was it is based on rocket parameters. Meaning this stuff. Okay? All right, so let me just come back to this and do one other manipulation. So I'm going to take this and do the following. So, also, dV equals minus v relative dm by m. There's that. I'm going to integrate this. And what I'm going to find is, if I integrate from initial mass to some final mass here. I'm going to bring this out front because it doesn't change. So I'm integrating this. This presumably goes from some initial velocity to some final velocity. And you'll remember hopefully that if I integrate a 1 over something term with respect to something, this is a logarithmic dependence. And this will tell us that the difference of velocities over some time interval, when I change the mass by a certain amount, is the following. Okay, so all I've done is take this, integrate it over some range of masses as I'm burning the fuel. This will give me a change in velocity, and I can figure out what the change in velocity is simply by looking at the ratio of the masses over whatever time interval is taken. Okay. Yeah. So, reasonable question, why is V relative a constant? I don't know anything about rocket design, but I imagine that for the most part people are, when they're firing rockets, they are simply powering these things up, and at that point they're continually going at whatever power they're designed for. So as long as I've got fuel, it's presumably true that the exhaust gas is coming out of the back of the rocket engine at the same constant relative speed relative to the rocket itself. Remember, this is the speed of the rocket relative to the exhaust gas. So I think that's simply a reflection of the fact once I power up an engine, it's always shooting out exhaust gas at the same speed. Okay? Now, presumably, of course, you could change that if you want, but the implication here is that you're designing a rocket for a certain power, a certain exhaust velocity speed, and if you do that, this stuff follows. Okay, so that's a built-in assumption. Yeah. Okay, so obviously I went a little quickly here, maybe a bit unfair. If I do this, and I did this integral, this would be logarithm of mass, and I would put in m final minus m initial. What you see here is I've actually got initial over final, which inverts the sign and gets rid of this negative here. All right. So I know that was kind of a little bit heavy going. I just want, before you guys leave, just a footnote. This is pretty much everything we're going to do on linear momentum conservation. We didn't get time to talk about centers of mass. That's a little bit relevant for some of the momentum conservation problems where we have one of two scenarios. An object that breaks up into multiple objects, or conversely, an object that starts out as two or more objects and coalesces into, let's say, a single object. So the idea of center of mass that we're going to talk about first thing on Thursday applies not only to momentum conservation, but as I said in the lead-in, it carries over into our discussions of rotation. Okay, we are good. I will see you guys later this week.
How people need to work on like body size. Yeah, I know this.
I'm just saying, like, yeah, I know it. Like, that's not the way to do it. sine A
Whatever mass
by sine B, and then you
that's what is the mass. It's not like the mass.
well that then you have like sine B times sine A and cosine B times cosine A, which you don't know how to do. Well.